Right. So let me get rid of this. Maybe I can switch off the video to get the better connection here. Okay. So the problem is to classify basis functions according to their symmetry. Yes. So we have group D4, which is a group of asymmetry operations corresponding to a square, perfect square. So we did this in the very first problem. So if you remember, we have a square like this. So maybe I should share a boot. So I have 4.0, 2, 3, 4 like this. And I have this diagonal D1, D2, and you cannot see the screen sharing. Okay. Okay, so then something may be wrong with your... Yeah, Lucas, could be something wrong with your computer or something. So can everybody see the screen? So if you cannot see the screen, please let me know. Okay, so let's continue. So we have this figure. You can have a look at this figure in the problem 1, the very first exercise. Yes. So this is X and Y. So that's the global coordinate axis. Now we put p orbitals on each of these atoms located at 1, 2, 3, and 4. And the p orbitals is just like x, y, z. Okay. So that's a spherical harmonics corresponding to L equal to 1, and that is equivalent to x, y, and z. So if I have a function equal to x, so we recall that can be written as ex dot r like that. So now if I perform some rotation on this function, that is by definition is equal to g minus 1 r. So that's equal to ex g minus 1 r. So that is equal to gex dot r. So you see that it's just the same as rotating the unit vectors, the Cartesian unit vectors, if you have x, y, and z as your functions. So we have 3 functions on each atom. So that means that we will have 12 basis functions. So that means that our representation will be 12 by 12. And if we look at the character table, this is obviously reducible because the highest dimension, I think, is 2. We worked this out before. So this is the problem then, is how to reduce this to the irreducible representation, how to reduce this representation, the 12 by 12, to a set of irreducible representations. So what we need to do is to look at the effect of each symmetry operations on the function. Yes. So let's take an example. So if I have AX, AY, would have D1, D2, and then C2, C1, C3, like this. And we look, let's say, at the, so we touch coordinates like this, x1, and this is y1. Here we have x2 and y2. So, and of course, we also have z1 and z2 perpendicular to the plane. Yes. And here we have x3 and y3. It's a bit crowded here, but you can see. And we have x4 and y4, like that. So these are the local coordinates. Now if we look, let's take an example of x1 and see what happens to these functions when we do the symmetry operations. So obviously with unit element, we just get back x1. Now if we look at ax, so what is ax? Ax is a rotation around the x-axis by pi. So this means that the x1 will be brought to x4. Yes. So if you just look at this picture, you can see that x1 will be brought into x4. So that will be x4. And ay is a rotation about y by pi. So then the x1 will be brought into minus x2. Minus x2. So we continue. Rotation about d1. So that's about the diagonal here. Then x1 will be brought into y1. So let me put it like this. And d2 will be rotation about d2. So that will brought x1 to minus y3. Yes. Minus y3. C2 is rotation by pi, I think, about the z-axis. So that gives me then minus x3. And C1 then gives me y2, because that's a rotation by pi by 2. So I will bring atom 1 to atom 2. And the C3 will give me y minus y4. Yes. And so on. You can do this. So for this example, we can just do this by inspection. And also for the home assignments, I think you can just do it by inspection, like what we are doing now. A more general way of doing this, more systematic way, would be to look at the local. Can I erase this? Yeah, I can erase this. We can also look at the effect of each symmetry operations on x and y. So the idea is that if I have if I apply a rotation our symmetry operation on, let's say, the x1. Well, this can be decomposed into two operations. So first I can rotate the atom. So I will write this as a rotation on the atom. Let's call it R1. That's the position of the atoms. And then I have the component of the along the axis. Yes. So we see that this just breaks up into sum of two rotations. First on the atoms. So this will bring, so Tg will bring me to another atom. And then we have Tg on the local coordinate or local Ex1. So what we have to do is that we just work out the effects of the symmetry operations on the x, y, and z in general. Yes, because this is true for any atoms. Yes, this part here is just a local coordinate transformations. So here I think it is a problem 1 in this exercise. You can see that if I x y like this, so if I apply Ax, so that's a rotation about x that doesn't do anything. If I make a rotation about y-axis, then this will be, the x will becomes minus x, and if I make a rotation along the diagonal, it will be y with this d1, d2 be minus y, and so on. Yes. So then, when looking at the rotations, the effect of the symmetry operations on the local coordinates, it's easy to do because I just figure out where the atom goes. So for example, if we take the example we had before, we take AX for example. So AX then will bring atom 1 to atom 4. Okay, so then this becomes X4 like this. You see what I mean? Yes, because if I have T4 here, if I apply T4 TAX here on X1, so that operation will bring the atom to atom 1 to atom 4, but it brings x to itself, x, so it becomes x, but then it brings this atom to 4, to atom 4. Yes, so if we take another example, if we take AY, yes, so AY, according to this table here, will bring, say I take TUY acting on X1, so it will bring X to minus X, and then it will bring atom 1 to atom 2, so it will be minus X2, and so on. Yes, so that's a more systematic way of figuring out the effects of the symmetry operations on the coordinates. But as I said, for the simple problems, we don't need to do it like this. We can just do it by inspection. But either way is fine. You can do both ways, depending on how convenient it is. So I have this list of functions here. So these are the bases. So this is the basis here. So I have the 12 basis functions. Centered at 1, 2, 3, and 4 atoms. And these are the effects. The table describes the effects of the symmetry operations on these basis functions. So now we want to calculate the characters of these 12 by 12 representations. So that's quite easy, because we just look at the list and see if the function is reproduced. So obviously, for the unit element, the function is always reproduced. So it will be 12. Yes. So the character will be 12. And if for X, we see that none is reproduced. So let me check that. Yeah. So if you look at the second column, this one here. So we see that none of the function goes back to itself. Yes. So, they are all different. So x1 goes to x4, y1 to y4. At least I cannot find anything equal here. So then the character should be 0. I think that's what I have here also. So here, character of the A is 0. And AX, AY, of course, is the same thing. If we look at the D, on the other hand, we will have one here. Oh, there's one here, so it's reproduced, except for the sign. And then this one here. I think that's all. Yes. So that would be then -2, like what I have here, -2 for the D. Yes. And so on. So if you look at the other elements, so let's check. Oops, what happened here? So if I look at D2, I should get the same result. It should be -2 because they belong to the same class. So let's check. This one here. And this one. So it's -2. Yes, it looks okay. So there are a lot of things you can check. Yes, if you don't get the same character for elements belonging to the same class, then something is wrong. And can also look at C2 maybe. You see that I think none of this is the same. So none of them is the same. So it's 0. Yeah. So this is the result of the characters here of this 12 by 12 representations. So now we can decompose this representation using the character table. So the character table is given here. That's a character table. And we just use the usual decomposition formula. Yeah, like that. And use the orthogonality between the character. We've done this before for the other problem. So we use this formula here to compute the coefficients. That's how many times the representation gamma, irreducible representation gamma, appears in this 12 by 12 representations. Yeah. So we just use this formula here. So we use the character table. So we know that's just a number of elements in the class K. This is the character of representation gamma of class K, or class K. And this is the character of the 12 by 12 representation. So just plug in the number. And if we do that, we get this number here. So 1, 2, 2, 1, 3. So for the representation A1, we get 1, A2, 2, B1, 2, B2, get 1, and E, we get 3. So let's count the dimension fits. So we have all of these, I think, is one-dimensional. It's one-dimensional, and this is 2D, two-dimensional. So then I have 6 plus 6, so 12. It fits. That looks fine. So are you with me so far? Is any questions about this problem? Okay. If not, then we continue with the next question. I think it is quite clear, as I can see. So now come the more tricky part. So we are asked here to sketch the Hamiltonian matrix. And we are supposed to figure out the largest block matrix size that we have to diagonalize. So what is this about? I mean, we remember that we have this result. This is basically the Wigner-Eckhart theorem, that if I have a Hamiltonian possessing a symmetry, then we say that this is just some constant. Let me call it A, just some constant here. It's not important because that depends on the potential of the system and so on. Then we have the part that depends on the symmetry. So this depends on the symmetry. Yes. So we say that the Hamiltonian is already diagonal. Yes. So even if beta is equal to alpha, the Hamiltonian is diagonal in the representation alpha. However, we see that we have several irreducible representations appearing more than once. So we look at this two here, it appears twice, and this appears even 3 times. So this formula here tells us that If the representation is the same, then this matrix element is not 0. So if I take phi alpha same, this is not 0. Yes. Even though psi and phi belong to two different irreducible representations. Well, they transform according to the same irreducible representations, but they belong to different blocks. Yes, yes. So this means that the largest size of the Hamiltonian that has to be diagonalized, that is the non-zero one, is actually 3 by 3, because that's this one here. So it is determined by the multiplicity, by this m here, that determines the size of the Hamiltonian that or the block matrix that you have to diagonalize. It's not by the size of the irreducible representations. So it's multiplicity, not by the dimension of the irreducible representation. It is an important point. Yes, that you have to think about. So if you look at sketch here, so we see that you have this kind of structure for the Hamiltonian. So I have the 2 by 2 coming from the A2 representations, and another 2 by 2 coming from the B1, because the B1 appears twice. And then I have the 3 by 3. Coming from the E representations. And the E representation is two-dimensional, so that's why the 3 by 3 appears twice here in the Hamiltonian. The Hamiltonian looks like this, and of course the way the Hamiltonian looks like depends on how we order the basis functions. Yes? If you order the basis functions according to the representations, let's say like this. So let's say that I have representation. Which one is it? So I want to show you. So what I want to say is that this form of the Hamiltonian here depends on how we order the basis functions. Yes. It is completely arbitrary. So I have ordered this in such a way that I have this thing with the same phi, which is not equal to 0. So in such a way that they then form a block. Yes, like this and like this. I don't know if you follow what I'm trying to say. You see, if I order this in a different way, then this non-zero matrix elements will appear in somewhere here and somewhere there. Okay, so it doesn't look nice. So I have ordered it in such a way that they appear together. These two basis functions with the same index I. Yes. Okay, so this is the first problem. Do you have any question about this? So the home assignment is very similar to this problem. I think it is the second problem or the first problem. Second problem, I think. It's a bit more complicated because the system is not a simple square like that, but there is no principal difference in working out the representations and calculating the characters and figuring out how many reducible representations are contained in the 12 by 12 representations. I think it is also 12 by 12, I think, if I remember correctly. Let's see what I have here. So, is there any questions or something which is not clear from this problem here? Okay, so if there is no question, then we can continue with problem 5. Maybe we should do problem 5. Yes, just looking at the home assignment here, it's a BF3 molecule with a D3H symmetry. The D3H symmetry is just a direct product of the D3 and reflection group. The reflection group is just isomorphic to inversion group or S2, same as the permutation of two elements. Then it's easy to figure out character table. Okay, so and we also have 3 p orbitals. So the orbitals can be anything. It doesn't have to be x, y, z. Could have chosen some more complicated functions, but then it's gonna be you have a problem with seeing. Oh, yeah. Let me see what happened here. Okay. I think just because I have not switched to the file. And so what I want to say is that I'm just going through the first assignment, yes, so you're not confused. I think you have a D3. Let me just draw it. And then you have, I think it's a boron atom. This is like this. So this is a D3H. So it's a D3 times. What do I call this? S, I think it's called the S. So we know the character tables of this. So you see, it seems a bit odd that we have a reflection symmetry, but this molecule is of course three-dimensional. So if you think about the electronic charge, then you realize that there is a reflection symmetry on the plane of this molecule. So now you have to choose your coordinate system. So this is up to you really how you do this.
Does that mean that in the assignment we can choose x4 and y4 however we want, and then the second line you gave us will not be the same?
And it will not be the same if you choose a different.
So it's okay.
Yeah, it is okay. Yeah.
Okay, thanks.
It's quite okay. Yeah, it's the one I gave in the assignment is just my own choice, a particular choice. Yes. But if you choose the different coordinate systems, then of course you get the different results. But it's perfectly fine. Yeah.
So does that mean that we get to choose ourselves in which directions x4 and y4 point?
I'm very sorry, but I cannot hear clearly what you say. It's a kind of echo. There's a kind of echo. Can you speak maybe slower, more slowly?
So should we choose ourselves in which directions x4 and y4 point?
Well, yeah, but I mean the x4 and y4 would be something like this. It would be natural. Like that.
But they can also be rotated, right?
Yeah, you can rotate it. You can rotate it. But I would say this is kind of natural choice. But yeah, it's up to you.
So then we get to choose in which direction they're rotated.
Yes, exactly. So that's why if you look at the table, let me see. How many examples? Yeah, so you see there is the, if you look at the x4 and the y4, there is this combination of x4 and y4 when you apply 120-degree rotation about the z-axis. Yes. So you do not need to follow what I have in there. But it would be nicer because then it's easier for me to check your your results. Yes.
But have you specified anywhere in which direction or in which direction they should be rotated?
I mean, so I kind of choose this like this, like what I have in the figure now. Yes, like this. And then for the local coordinates for the F atoms, what was the suggestion in that? I think I suggest something here. So you take the line. Sorry, this is the first problem.
But which F atom is F1 and which one is F2 and which one is F3?
Yeah, so as I said, it doesn't really matter. Yes, how you choose, how you label the atoms and how you choose the coordinate systems. So maybe I should have labeled this 1, 2, 3. So usually I label it counterclockwise, something like this. So 1, 2, 3, like that, for example. Yes, so it doesn't matter where you have the one, as long as you have the cyclic, for example, you 1, 2, 3, like this, clockwise, anti-clockwise, and usually this anti-clockwise. So you see that the x1 is brought to x2. So atom 1 is brought to atom 2 when I rotate by 120. So you can kind of guess from the table that this is the ordering of the labels. Is that okay?
Yes.
Yes. Okay, good. It's up to you. Yes, how you want to label. Okay. But as I said, it's easier for me to check your results if you use the same ordering. So maybe I should have indicated in the problem. But I kind of assume that labeling is anti-clockwise, and that this is the choice of the coordinates on the boron atom. Okay. Is there any other question? So if there is something not clear about the home assignment, yeah, just send me an email and ask me. So, because it could be that I missed something or I was not very clear, and just send me an email.
There's one thing I was wondering about, although I was wondering about how to calculate the translation of gamma.
Translation of gamma.
As to
what do you mean by gamma?
the same way you did in the first exercise when you calculated the gamma of all, the total of all representations.
Let me see if I understand. Oops. You're talking about gamma, M gamma, you mean?
Yes.
Here?
Yes. Although I was more wondering how one does it when there's a dipole moment on the symmetry, meaning that you have some linear function, x, y, or zeta.
Yes. So you're talking about second part of the problem.
Perhaps.
Let me see if I... Yeah. So I think the question is to work out the linear combinations, which transforms according to the identity representation. So if you have then a dipole field, so the dipole field then would be you have to figure out which representation that type of field correspond to.
Yes, exactly.
Right. So you have to figure out which irreducible components the function, let's say x, contains. So it doesn't, okay, so if we take the x, I think it was x, let me check. Yeah, so in the x direction. So you have to figure out what is contained in x. What are the components, the irreducible components of the function x? So you have to use the projection operator to figure out the component.
Okay, I think I understand.
You understand, yeah. So you figure out, yeah. So you have this, again, this is the Wigner-Eckhart theorem, yes? So you have this alpha I, and then you have this operator, beta, and then you have some other function, gamma, like this, like that. So I think we are told that this is according to the identity, and this is a dipole, so it's x. Yes. So then you have to first, well, so you have to figure out which representation this dipole operator corresponds to, and then from this direct product representations, you can easily figure out which states is non-zero, which irreducible, which states belonging to which irreducible representations, which are not zero.
Okay. I hope that we will go through the example 5.
Yes, wait, it's already 5 minutes fast. Okay, so maybe we should have a little break now, and we come back around 10:15. Yeah. Okay, then we continue with problem 5. So let's continue with problem number 5. Okay, so maybe I just continue this unless group 6 would like to have a go. So not, and what happened here? Something funny with my computer. Okay, back again. Let's do number 5 here. Yes, so we are supposed to work out the vibrational modes of water molecule. So we are given the character table. So it's relatively simple because the representations are all one-dimensional. And we are given the coordinate system here. So this is a particular choice of coordinate systems. Yes. So the reason for choosing it this way is that it makes it easier to recognize the vibrational modes, because I know from a physical ground that there should be some vibrations along this line here and along this. So you can imagine the hydrogen molecules vibrates towards the oxygen atom. That's one possible vibration. So this is just a particular choice of the local coordinates. So I could have chosen something like this for my x2 and then y2, and like that. That's also fine. But if you do it like that, then it would be more difficult to recognize the normal modes. For this case, it's actually not so difficult, but anyway, this one is kind of easier to see what's going on from physical point of view. So again, for this molecule, we assign coordinates, Cartesian coordinates. So for analyzing the molecular vibrations, we always have to assign these coordinate systems, these Cartesian coordinates, not some arbitrary functions, but these Cartesian coordinates, because we are looking at the vibrations, because we want to study the vibrations of the atoms. It's the positions of the atoms, how they change when they move away from the equilibrium position. So these are the coordinate systems, and then we just apply the symmetry operation on each of these coordinate systems. So I think it's kind of clear here. So let's take, for example, take the C2 here. I need a figure here. Okay. Okay, so I'll look at C2 here. So C2 is just 180-degree rotations around the y-axis. Yes. So we have this global coordinate systems. We are looking at the rotation about the y-axis. So then we see that x1 will be brought into minus x2. Yes, because when we rotate the atom, the hydrogen atom here, it will end up there, but x1 will then point this way. Yeah, so that's minus x2. Y1 then will end up same as y2, so that's nice. And z1 will change directions because z1 is perpendicular to the plane, so z1 will be upwards towards us, but when we rotate, it will go downwards, so that's why it becomes minus z2, because z2 is also defined towards us, yes, and so on, yes, with the other coordinates. So it's quite straightforward to work out all these effects of the symmetry operations on each of the coordinates. So again, we have the reflection symmetry on the plane, on the plane of the molecule. And again, that looks strange if you think about this as a two-dimensional object. What does it mean, reflection? But here we have to think of it as a three-dimensional object. We have a charge density. So the one way to think of it is to imagine the charge density of this molecule. So it has a symmetry, reflection symmetry on the plane. Yes. So I think it is, which one is it? Cannot remember which is which. I think it is this one, perhaps. Yeah. Okay, so we have this table here. I think that's similar to what we did before in the second problem. So now we can decompose the representations. So we have 3 atoms, so that means 3 by 3, so that's a 9 basis functions. So it's a 9 by 9 representation. We can decompose that by first calculating the characters, and the characters can be just seen, can be just read off from this table here. From this table, we can easily calculate the characters as before. So for the unit element is obviously 9, and for C2, so we just look at which is brought to itself. So we see that this one brought to itself, so minus 1, 1, and minus 1. So then minus 1, minus 1. Okay. And for the sigma V, we have this one. Oh, all of them are brought to themselves. Well, kind of clear because it's a reflection on the plane. With some, then we have 3 because we have 1 plus 1 plus 1 minus 1. So that's 1, and the same for the others, and it's 3. And also for the reflections on the plane, bisecting the hydrogen atoms. I mean, in the plane in between the 2 hydrogen atoms. So that's a reflection, this one here. And that if we look at this table here, we see that this thing is brought to themselves. So that gives me 1. Yes, because it's minus 1, 1, and 1. Okay, so that's quite clear and similar to what we had before. So then it's straightforward to calculate how the decomposition. So again, we use this formula. Orthogonality between the characters. And if we do this, we find that we have, for the representation A1, we get 3. for A2 we get 1, and for B1 we get 3, and B2 we get 2. So all of these are one-dimensional representations. So we check the number, should sum up to 9. So 3, 1, 3, 2. So that's 9. So that's fine. So I guess it's fine up to now. So no funny things here. It's just quite straightforward. Okay, so now the next question is, we are supposed to use the projection operator method to find out which linear combinations belong to which irreducible representations. So we just apply the projection operator. We apply projection operator, this one here, onto each of the basis functions. These are our basis functions here, and 9 basis functions. So we just use the character table because we need to know the character of each of the irreducible representation. And we use the other table that we worked out for the effects of the symmetry operators on the function. So we look at this. See, so we use this table here to calculate the result of projecting onto a particular irreducible representation. So maybe we can do one example here. So let's see, we take just a simple one like the PA1, so that's the identity representation. So all the characters is equal to 1 because it's an identity representation. And if we look at the effects of the symmetry operations on x1, what do we have here? Let's see. So we go back here. So it goes to x1 and then minus x2 and x1 and then minus x2. So then it becomes so then it becomes so difficult to write this. So it becomes 1 happen here. So 1 divided by h, which is 4, and then I have 2x1 minus 2x2, like this. It's because if you look at the effect of the symmetry operation on x1, we get x1 and then minus x2 and then x1 and then minus x2. Then if I use this formula, I will get this result, which is this one here. So the factor here in front of the linear combination is actually not important. So I could have just dropped that. So just write x1 minus x2. So, by the way, I think Daniel pointed out to me last night that in the home assignment, there is a factor of 2 difference for the, I think for the first problem. Yes, for problem 1D. I think I probably made just a mistake. There should be a factor of 2 for this factor. But that factor is not important anyway, so it doesn't matter. You could have just forget this factor here and just apply that one and remove any constants. So for example, this thing is twice of 2x1 and minus 2x2. Well, I can just write it as x1 minus x2. Because what's important is the linear combination, not the normalization constant. These are just some normalization constant. Okay, so this is what we get. We apply this projection operator on the functions, each of these basis functions. So is there any question about this? Is clear? Yes, I think it is quite clear, right? We can take another one if you like. We can take the B1. What happened to B1? So B1, we look at B1 is 1 minus 1, 1 minus 1. Okay. So then we get x1 plus x2 because we have the character is 1 minus 1, 1 minus 1. So if I multiply this, then we get x1 plus x2. And so on. Yes, it's quite clear, I think. Okay, so now we have this projection. I think it is worth discussing this a little bit. So if we look at the A1, the column A1 here, this one here, we see that there are 3 independent combinations which transform according to A1. So we have this one, and this one. Yes, those are the 3 independent combinations, and that is consistent with what we have here. So we have 3 of them. So that there should be then 3 independent functions, which corresponds to the multiplicity of the representation A1 contained in the 9 by 9 representation. Okay, and if we look at A2, see A2 there should be just 1, and yes, there's only 1 for A2. We only have Z1 minus Z2. That's the only combination appearing in the irreducible representation A2. That's again consistent with the fact that we only have one representation. So we just have 1 representation here. And for B1 we should get 3. So let's check that. B1, okay. So yes, there are 3. So x1 plus x2, y1 minus y2, and x3. So these are the three independent functions or linear combinations that transform according to representation B1. And for B2, 2 should be 2. Yes, there are 2. So for B2 we have 2. This one and that one.
I'm guessing it doesn't matter which. I mean, there's a so-called degeneracy in your choice.
You mean?
I could, for example, choose the x in the x2 row, x plus 1, hello, x1 plus x2 instead of the first row.
Yes, they are the same. Yes, they're
Okay.
identical.
Yeah.
So you mean this one here and that one?
Exactly.
Yeah, they're the same. Yes, so we choose one of them because they are. I mean, the number of basis functions is of course much larger generally than the number of functions that transforms according to this particular representation. Yes. So it is it's possible that you the same let's say it's x1 and x2 happen to project to the same linear combination with respect to b1. Yes.
And the constant before the term doesn't.
It doesn't matter.
Yeah.
It's just a normalization constant. Okay. So you could just drop it. What's important is the combinations. Of course, the relative coefficients like x1 plus x2. This coefficient 1 and 1 is of course important. Yes. So, but the constant multiply the whole thing is just a constant. I mean, it's just a normalization constant. Yes, so we have this. So everything so far fit with what we expect. We have this decompositions, and it fits with the fact that we have the same kind of compositions also for the basis functions. It should be, because if you think about this as again, I have said this many times before, that you make a rotation, yes, by using the Clebsch-Gordon coefficient. Well, it's not a Clebsch-Gordon coefficient, but just the s minus 1. So that this is the 9 by 9 then representation. And what we have done here is we decompose this into the various irreducible representations, like we have discussed several times before. Okay, so now we continue with number 4, question 4 here from 3. Verify geometrically that there are 3 transitional motions and 3 rotational motions corresponding to 0 frequency. So transitional motions just means that the whole atoms move together. So there is no relative displacement between the atoms. So there's no vibrations. It's just the whole thing moves. Yes, the whole atoms, no vibrations. So there are then the 3 translational motions along x, y, and z, because there are 3 independent motions. And that's also the 3 rotations about the Cartesian axis. So there are 6 motions which have 0 frequency. And then there will be then the remaining 3 which correspond to vibrations. So there will be 3 vibrations with non-zero frequencies. So let's figure out first the translations. So I have it here. Yes. So let's see, translation. Translation just means then I have, let me actually, okay, so I have this molecule, this is the oxygen here, and then I have the small hydrogen atom there. So let's look at the translation along the x-axis. So that would be my x3. And it goes like this, and it goes like this. So now we have to be a bit careful because we have chosen the coordinate system, something like that. This is my y2, and this is y1. And let me check that I got the right direction. So this is x1, and this is, oh, sorry, it should be like this. Ah, I'm so that was stupid. Can I go back? Yeah, good. Okay, so this is, let me restart. Okay, so this is y2 and this is x2, like this, I think. Yes, so now we see that this motion of the hydrogen atoms along the x-axis is actually a linear combination of x1 and y1. Okay, so whereas the oxygen atom is just x3, yeah, because the y3 is perpendicular to the direction of motion. So then the linear combinations corresponding to that translational mode is x1 plus a little bit of, or not a little bit, not necessarily a little bit, depending on the angle here, depending on this angle, but it's a combination of x1 and y1. Yes, for this hydrogen atom, for the first hydrogen atom, and the same for the second hydrogen atom, except that it's minus because it's going opposite to the y2 direction. Yes, if you think about the projection of these on y2, yeah, it's in the opposite direction. So if you look at this, it is here. This is the projection of the motion along the y2 axis. So it's minus. So that's why I have minus here. But this is the combination then that corresponds to translation along the x-axis. Yes, x1 plus constant a y1 and x2 minus a y2 and then x3. x3 is just x3 because so the y3 is not involved. It's perpendicular to the motion. And if you look at the table that we generated for the projections of the basis functions on the different representations, we see that these particular combinations of functions belong to B1. Yeah. So let's have a look at that one. So let me erase that. So x1, x2, x3, and then y1 minus y2. Yeah, so you see that we have x1, x2, x3, and then y1 minus y2. So that particular combination belongs to B1. So we can then say that the translational motion along the x direction belongs to the B1 irreducible representation. Okay, so now we can maybe take another one. I think we have time. Okay, so let's take another one here along the y. Oh, I should have done the, okay, I can easily draw it again, it's no problem. So this is my, if we look at the motion along the y-axis, so then that would be just a y3, and we have a motion like this. But this motion of the hydrogen atoms, of course, has components along the x and the y. Yes. So we have the y1 here, and let me see, x1 here, and I have y2 here, and x2 there. So we see that for the first atom, it should be minus x1 because it's going away from the projection of the motion is the minus x1, and then plus y1. Okay, so that one and that one. And for the second hydrogen atom, it's both positive, so both positive, x2 and y2. And this coefficient A is just some positive number because it depends on the angle, yes? The angle, this angle. And it's just the ratio between the x and the y. And for the oxygen atom, it's just y3 because it moves along the y direction, perpendicular to x3. And then if we go back to the table, we see that it is, this combination belongs to A1. So let me try to remember this, y1, y2, x1 minus x2, and y3. Okay. So it says A1. Yeah, so that's what we have, yes. x1 minus x2, plus a2, and y3. That fits, and so on. So we'll think about the z is easy, yes, the z, and then it's just this, the sum of these three, yes. So let's look at the rotation. So this is rigid rotations. The whole atoms rotate. There's no relative motions between the atoms. So if we take the rotations, a little bit more complicated, but not so difficult. I mean, I have this oxygen atom here. So we have to look at the center of mass, maybe somewhere here. I don't know, somewhere there. So we rotate, then it will go like this. So it will go like this, and it will go like, it's not a very nice picture here. Let me make it nicer. A bit more even, symmetrical, like that. Okay, so then it's perpendicular to that one, goes like that. Okay. So if we look at, let's say, the motion, the rotation along the about the z-axis, this one. So we see that we have a component x1, x2 coming from this and that one, and also y1 minus y2. I think minus y1 because we define this way to be my y1, and this is y2. So there's a component along the minus y1. So that's why I have minus y1 here. Okay. And for the oxygen atom, it's just x3. And then if you go back to the table in the previous page, and you can see that this particular combination belongs to B1. So that's how we figure out all these translations and the rotation modes, zero frequency.
I have a question.
Yes.
Now I've noticed a similarity to Wagner-Eckert theorem, so I was wondering if one can use that theorem to derive to the solutions, at least in the terms of the modes.
Let me see, what do you mean by this? Is the Wigner-Eckart theorem. So I have not thought about this before, but in what way you use the Wigner-Eckart theorem to figure out these modes.
Since if we take the translation as an example,
okay,
then, well,
so we have the Wigner-Eckart theorem like this. It tells us this kind of matrix elements, right? So what is your point here? So I'm trying to understand what you're trying to say.
Perhaps it was nothing. Yeah, I just had a gut feeling that you could use it if you change O to the translation, and then the first, the ket bracket will, yeah.
I see.
It transforms in a similar way to the group symmetry. So you could take out a matrix representation from that one.
Okay. Yeah, I've never thought about doing it like that. It may be possible, but I don't see immediately how to do it. Like,
no, it's just speculations.
Okay. Okay, let's think a little bit about that. But yeah, so this is the way we usually analyze the motions. Okay, so maybe we should look at the remaining modes. So there are 3 remaining modes, and that is this 2A1 plus B1. And I have drawn the result here. Yes. So these are the 3 combinations belonging to A1, the 2A1, and another one belonging to B1. So it's kind of intuitive physically that you will have a kind of stretching. Is in the stretch mode sometimes called. Because all the atoms moves. So of course this vibrate like this, yes. So there's particular combinations. So I have written it for the stretch out case, but of course you change the sign, so then it will be stretching in. So the actual vibration will be like this and like this. Yeah. The atoms vibrate in that fashion. So that is this combination here. And then if you look at the other combinations, and then you have this one here. So that would correspond to this type of motions. So you have the 2 hydrogen atoms kind of approaching each other, or vibrating, and then the oxygen atom will again vibrate like this. And there's a third one here, which is a little bit more difficult to guess from physical consideration, but you have this motion also. So so the symmetry can tell us how these vibrational modes look like. Of course, we cannot calculate the frequency because the frequencies have to be determined by diagonalizing the dynamical matrix, because that depends on the strength of the forces between the atoms. So we do not know this coefficient here, A, for example, that has to be determined by calculations. Yes, that also depends on this angle and the force between the atoms. But group theory can tell us how the symmetry, kind of imposes some constraints on the motions of the atoms. So only certain modes are allowed by the symmetry. You have to fulfill the symmetry. Yeah. And these are the three possibilities. Non-zero frequency. So these are the non-zero frequency of vibrations. So in the home assignment, it's a rather similar problem, except that it's a bit more complicated because you have it's ammonia atom, a molecule. I mean, you have, let's say this is the nitrogen, you have the hydrogen here, and then you have hydrogen here, and you have another hydrogen atom here. And like that, I guess. And this, and if you draw projection on the plane of the, it will end up at the center of the equilateral triangle. So this is an equilateral triangle. I think you have seen this molecule. Yes, it's a famous molecule. You can easily Google it and find the shape. So it's just a tetrahedron, but it's not a regular tetrahedron because this is a nitrogen atom, not a hydrogen. So again, it's really up to you how you choose your coordinate system. So one suggested in the home assignment is to choose the y-axis along this line here, the y-axis along that line for the hydrogen atoms. Yes, so it's similar to what we have here for the water molecule. That you choose one of the axes along this line. So let's say the y-axis, but could be also the x-axis, it doesn't matter. So the choice of the coordinate system is entirely arbitrary. So the results should not depend on how we choose the coordinate system. But it's often important to choose a good coordinate systems because otherwise it's difficult to interpret the results. I mean, suppose that I choose funny coordinate systems. Let's say that for this water molecule, let's say that I choose. Suppose I'm crazy enough to choose coordinate systems in which the z-axis is not perpendicular to the plane. Let's say because like this, and the y-axis like this. And then the x-axis, I should get it right here. So it should be like that, for example. Of course, one can choose it like this, but then it gets so complicated that it's difficult to recognize the normal modes. But if you do it properly, if you do it correctly, you should get the same answers. You should still get this right modes, but with a much more effort. So we don't want to torture ourselves. So we choose a simple coordinate system as possible. So this particular choice for the water molecule is a kind of physical choice because we kind of expect that there will be this kind of vibrations along the lines joining the oxygen and the hydrogen atoms. And similarly here, that's why I suggested to choose the y-axis along the line joining the hydrogen and the nitrogen atoms. And for the x-axis, you choose to lie along the plane of the hydrogen atoms. It's well defined, yes, if you do that. And it's kind of nice. But you don't have to do it that way. You can choose your own coordinate systems. If you find a better one, then you can just use it. Okay, is there any questions about this? I think the home assignment should be relatively maybe not straightforward, but it should be doable. Yes, yes. I will upload the solution. Yes, I will upload the solution. You can have a look in more detail at home, because especially these two problems, number 2 and number 5, is particular, are very much related to the home assignments. So you can go back to it if you have difficulties. So, is there any things which are not clear or you want to ask? Can of course ask later if you have questions. Just send me an email. So I hope 1 week is yes. Yeah.
I have one question, but it's not related to the course. I was thinking, if nobody has any questions about this group theory, I would like to, if you have time, ask something about DFT, just very briefly.
Okay. So you're asking about density functional theory?
Yeah, but I have like one slide. If it's just a band gap, I want to know your opinion about it.
Okay, but maybe we can just discuss this by ourselves then, because this is not.
Yeah, I was just thinking if nobody has like questions about.
Or you can just send me an email, whatever.
Okay.
Or you want us to do it now? Or?
Yeah, I have like one slide if I can share it then.
Okay, so let's say to everybody that we finished the exercise class today. Yes. And as I said, if you have questions, just don't hesitate to ask. And so I hope we have enough time to do the assignments. I think it just takes, I would say, just 1 day or so. I think you can do it in 1 afternoon, I would say. I think you know how to do it now, so it should be quite clear. Okay. So bye now, and there's a message from Daniel. Yes, I think the oral exams, the dates for the oral exams, or the period rather, is written in the website. Yes. I think it is just a week after the end of the course. So it will be at the same time as the second part. Okay. Good. Okay, let's see. You have a question?
Yeah, can I share? Can you see this? The title is LDA DFT bandgap. So I was thinking, because I run this like a band structure simulation. Or first, I want to say I optimized the geometry, and I get 2% smaller lattice constant than experimental.
Yeah, that's not surprising. That's a usual LDA problem, I think.
Okay,
it's a little
not
bit
like not too small. What would you say this is like too much off from the experimental?
2%, but I think that's a typical error in LDA. Okay. It tends to underestimate the bond length, so that carries over, I think, to the solid. And if you use GGA, it tends to overestimate.
Okay.
So that's a common problem, I think.
So it's a common problem. So it's not that my optimization is somehow wrong.
No, I don't think so.
Okay. And then, well, I've taken the electronic structure theory course, and you talked a lot about how this LDA underestimates the gap.
That's right.
So I was very much expecting, like I have the gap here at comma point for indium antimony. So I was very much expecting that this band here is like joined with this.
Yes.
But I do get like exactly the experimental gap.
Okay. I mean, of course, in some particular cases, it's possible that you have agreement with the experiment. It is a bit surprising to me, though. It is very small, though. The gap is only 0.17.
Yeah.
So that means could be an error. Could be computational error in the. Well, but you use quite a bit of K points, 8 by 8, so that should be accurate enough, I think.
Yeah.
But yeah, I mean, it's not an absolute thing to say that generally LDA underestimates the band gap. Yeah.
Because I don't really know that much about this like cutoff and this. I mean, in papers I see it that I get no gap, or other papers, but I use very simple like exchange correlation and very simple.
So that could be, yeah, see, when your gap is so small like this, then the small things can alter the results. Okay. So like number of key points or the cutoff. So you probably have to check the convergence.
Okay.
So you should increase the cutoff energy and the number of key points. So the number of key points looks quite large here because this is almost like an insulator, right? Or is it a metal? Well, you have a gap, of course, but
it should be a semiconductor with the.
It's a semiconductor, yeah. But there was a small gap, so that's almost like a metal.
Yeah.
But still, 8 by 8 is quite large for an insulator, for the semiconductor. But the cutoff could change the results. Yes.
Okay, because I think the pseudo potentials they use, they are like ultra soft.
Yeah, so that could be another factor. I don't know if you have access to all electron code, band structure code.
Okay, not sure. I use this Abinet.
It is Abinet, okay. There is also this all electron code. You can actually get it for free, but you have to register. I think it is from the Jülich group in Germany. It's called Fleur. Fleur, like the French for flower.
Okay.
So if you Google that, you will find the home page, and then you just write to the guy who takes care of the code to provide you access to the. It's free. You can download it. So that's an all-electron code. Should be more accurate than the ultrasoft.
Okay. I can vary the pseudo potentials here, but I'm running this on my computer, so I've done very simple.
I see.
But then the another problem here is that I always get the Fermi level inside the band.
So then it's actually a metal.
Yeah, but then I read somewhere I can just shift the Fermi level. Otherwise this looks very good here, but then the Fermi level should really be here, like in the gap.
I see. So, so this is a very tiny thing because it is so small that you can easily get different results depending on your choice of the convergence parameters. Like the cutoff energy. I would guess it's the cutoff energy which is problematic. Yes. So let's see. This is indium antimonide. Yeah. So the question is, so where is it in the periodic table?
It's 3.5.
3.5, yeah. So that should be okay for pseudo potential. It's not like a 3D or something. Yeah, but still, pseudo potential sometimes is a bit problematic. Yeah.
Okay.
Because
I was trying to read about this Fermi level, and they said that the DFT usually gets it wrong, and then you can just shift it. But I don't know if this is correct. And then somebody talked about gauge freedom, but I don't really know what I mean by this.
No. Well, I mean, if you shift it, then you get the wrong number of electrons, no? Because you will occupy more states. So you cannot simply shift the Fermi level.
Okay. The DFT should give the correct Fermi level.
Well, I mean, you mean there's a theorem? I mean, there is a theorem for a finite system that the highest occupied Charm values is eigenvalue is the correct one, but this is LDA, yes, so it's not the exact functional. So the Fermi level can be wrong in LDA.
Yeah. Okay. Okay.
So I would suggest you. Yeah, I don't know how much time you have because this is your master's thesis, as I understand.
Yes.
Yeah. So
I'm kind of done with the simulations, but I wanted to, or I can like rerun them, but I wouldn't want to change the code anymore.
I see. Yeah. Well, if you have time, it's worth, I think, using all electron code.
Okay. Yeah. But also, I'm not that interested into this this band gap electronic structure. I'm doing phonons and nonlinear optics.
Okay.
By this density functional perturbation theory. Do you know anything about this? That if I'm here, like if the band structure here is wrong,
yeah, I mean that could
follow
affect
me everywhere.
Yeah, it could affect the result. So when you have a wrong Fermi surface, right? And you know the phonons is very much affected by the shape of the Fermi surface because it's such a small energy. So it's on the transitions around the Fermi level is very important. But of course, it depends also on how many states you have at that Fermi. Maybe it's not so important that particular gamma point. You don't know.
Okay.
Okay. Is there any other questions?
No, I think this is all. I just wanted. I'm working in an experimental group, and I cannot really like verify any of my simulations with anybody. So.
Okay, so you're working with the experimental group.
Yeah.
Okay.
They have a nice experimental setup, but they told me to do the simulations and then.
Well, it could be interesting.
Okay.
Very good.
Well, thank you for your time.
No problem. Yeah.
Okay.
So, see you then.
Yeah. See you. Bye.